my name is Jeffrey Kramer. Thanks a lot for giving me the opportunity to talk today. I'm kind of an outgoing graduate student here at the University of Minnesota. Just finished up my master's thesis dealing with our two-stage ditch here in southern Minnesota. Been working on that for a couple of years, and now currently looking for a job and kind of helping tie up some loose ends and carry our analysis a little bit further from what I was able to do with my thesis. So talk a little bit about our project today, and most of it's going to focus on a little bit of work I've done with relating to two-stage ditch economics. So I'll get going. All right, so here is just an overview of our project site in southern Minnesota. We're very close to the Iowa border in Mower County, and it's about it isn't a private drainage ditch. There's quite a bit of issue trying to find a good site. We originally were working with a public drainage ditch, and there was quite a bit of reluctance on the part of the drainage commissioners to allow us to work on that project. It was near a city of about 20,000 people, and there'd been a lot of flooding issues there, so the private ditch ended up working out a lot better for us. It cleared up a lot of the red tape. So our watershed is just over 12 square kilometers, and it's a very kind of typical southern Minnesota landscape, basically corn and soybeans, almost exclusively. And our work started in spring of 2009 with some original site surveys, and then kind of carried through the summer and the fall with our design. And then construction took place in October and November of 2009. Then I've got just a few pictures to share here. These are from the spring of 2009, just showing what the ditch looked like beforehand. This is very standard trapezoidal ditch. Show a couple of the issues here that we found. Quite a bit of deposition going on here, and you can see also some of the bank sloughing that was happening kind of on the right bank here. And also there's a kind of a better shot of the bank sloughing. That was a big problem throughout much of the ditch. And then just a few pictures from construction as well. Here, this is kind of the beginning, one of the first couple days when they were started working on the north end of the ditch. So I know the previous presenters had kind of talked about the ratio of the kind of the flooded width, I guess is what we call it. And we ended up going with a 3-to-1 ratio as well. Obviously for reasons that were mentioned earlier, just to kind of reduce the amount of agricultural land lost. And there's just a shot of some of our erosion control measures. And here's one of the best pictures we have of kind of what we're seeing now in 2010 and 2011. This is kind of what we saw the first spring after construction, and you can see there's hardly any vegetation. It's all very low grasses. By this time, throughout 2011, we've had really thick vegetation come up, and it's become very well established. And just wanted to highlight a little bit of the work we've been doing. I don't have a lot of time to talk about it, unfortunately, but one of the things has been geomorphological monitoring, looking at cross-section surveys at 7 different locations throughout our ditch. I guess maybe I forgot to mention when I was showing the project site that it's about a 6,000-foot reach. So we have 7 cross-sections throughout that 6,000 feet that we've measured 3 times thus far. Probably get out again this fall to kind of see what's been happening. And then we were looking at the longitudinal channel survey as well, kind of trying to see if we're getting any aggradation, things like that. And we've been doing a pretty substantial amount of water quality and quantity, I should say quantity, monitoring. Been measuring precipitation, inflow and outflow in the ditch section with flumes. We've been measuring tile drainage flow, and then quite a bit of water quality information. Been primarily focused on nitrate end measurements. We have a couple of Hawk portable probes that we use, so that makes it really nice for gathering a lot of data in a short amount of time. Kind of our main goal was to get at the nitrate removal, the nitrate N removal in the ditch system, just to try to see how much improvement we're getting over the pre-existing ditch. And then there's also been quite a bit of work done with kind of trying to characterize the vegetation in the ditch. And then also the final thing is an economic analysis that I did as part of my thesis work, and that's kind of what I'm going to be talking about mostly today. And I'll kind of segue into the economics. Here's just a breakdown of the costs on our project. You can see that I was a little bit surprised by this. I guess that excavation actually ended up being less expensive than all of the work we did with replacing tiles and side inlets, and also erosion control was more expensive. That was kind of the most expensive single component, and then we had seeding and sort of other miscellaneous costs that were fairly minor. But it ended up being an overall project cost of $33 per linear foot. And then I just pulled some numbers out of the literature for other two-stage ditches that have been constructed. Most of these are in more of your neck of the woods, but you can see it's a pretty wide range of construction costs. It's kind of surprising, actually. It goes all the way from $10 per linear foot up to $68. So you can tell that this really varies quite a bit. So moving on to my economic analysis, all this is based on a spreadsheet that was developed by a professor that works with us here at the University of Minnesota in applied economics named Bill Lazarus. Talk a little bit more about basically what the spreadsheet does is calculates the net present value of the existing trapezoidal ditch, and then also calculates the existing net present value for a proposed two-stage ditch based on a number of factors. I think probably the most important one is the interest rate, or the discount rate as it's called. The project life is somewhat important as well. And then for conventional ditch, the main factors are clean-out cost, how much is it going to cost to do periodic maintenance, and then also how often is that going to need to take place. And then for the two-stage ditch, the main costs are the construction cost and the adjacent land value, basically reimbursing farmers for their lost acres of production. And so just wanted to go over a few of the assumptions for the analysis that I've done. We used a 100-year project life, and then I was kind of a best case scenario, just assumed that there were negligible two-stage maintenance costs, and assume that the next conventional or trapezoidal ditch cleanout would actually be next year, I guess, which was kind of a reasonable situation. I guess in our experience anyway, that the ditch that we constructed was due to be cleaned out very soon. So, and then basically just to simplify this analysis, we ended up kind of assuming that that erosion control costs and then the tile and side inlet replacement and spraying and seeding, all of those costs would basically be equal for trapezoidal and two-stage ditches. So that really simplified the analysis. It might not be entirely realistic, but it was something that we kind of needed to do, and I think it is somewhat reasonable just to kind of get a grasp on the kind of the basic economics. And so just before I show you the results, I want to kind of try to explain it. It gets a little bit complicated with all the different variables that we're using. So the initial results are presented as a break-even discount rate, which basically we use the spreadsheet to determine the interest rate at which the net present value of the trapezoidal ditch and the two-stage ditch are equal. And then, so obviously, if this can be kind of used as a tool for an engineer or someone maybe with the Nature Conservancy, something like that, to decide if we can make this happen. If we can get an interest rate below 5% or something, then we can make this happen. If not, the conventional ditch might be economically more preferable. So here's the kind of the first set of results. So this shows a little bit of a busy graph, but you can see on the x-axis here these are different trapezoidal ditch cleanout intervals, and then each of the curves corresponds to a different agricultural land price adjacent to the ditch. And then the results on the y-axis are the break-even discount rate. So you can see below all these curves, if you're able to achieve a lower interest rate, the two-stage ditch is going to be preferable. And so just a quick example here, if you imagine you're at $5,000 agricultural land cost, and you're cleaning out your ditch every 12 years, your break-even interest rate is going to be about 4.5%. And if you take the same conditions, but you're cleaning out every 9 years, you're going to be around 6%. And so it kind of shows just how important some of these factors are. I mean, even cleaning that ditch out a little bit more often is really going to help the case for a two-stage ditch. And so this first graph also I didn't mention was for $5 per linear foot two-stage ditch construction, which is a little bit sort of optimistic. And then the next graph I have here is for $15 per linear foot for two-stage construction. And so you can see that the picture becomes a little bit bleaker in a hurry if you move up to $15 per linear foot. And so just a summary. There are going to be certain situations where, if you're cleaning out a ditch, every 5 or 6 years, which I don't know that happens very often, but if you are, it's going to be a pretty clear case where a two-stage ditch is probably going to be economically preferable. Also, if you have a site where you can kind of reach a low two-stage ditch construction cost, that's going to really help the case. And also low discount rate, interest rates, which really play an important role. And so we realize that for a lot of ditch circumstances that this initial analysis might actually lead people to conclude that a two-stage ditch probably isn't economically feasible. And so we decided to kind of take another analysis where we looked at, okay, for these situations where the net present value of the two-stage ditch is actually higher than the conventional ditch, how much subsidy would actually be required to kind of bring those net present values to the same level. And so just kind of an idea, and some ideas that we have of potential justification of subsidies. The main one really is water quality benefits, whether or not that's maybe sediment or nitrogen or phosphorus, things like that. Also, it could be just enhanced ecosystem within the ditch, and also a more pleasant landscape that might be valuable to people. And so just a quick overview of this, sort of the results I'll present here. Rather than a break-even interest rate, we're presenting this as a break-even subsidy. So that means that's that subsidy that's required to bring those net present values to the same level. And the costs here are reported as a one-time subsidy. It's the present cost that would be necessary at construction to make the two-stage ditch feasible. And so you can see for the $15 per linear foot case, you can see that the subsidy is actually quite high in a lot of cases. In the same example, if you look at maybe 12 years and an interest rate of 5%, you're looking at right around $10 per linear foot. For a project the size of ours, that would have been $60,000. So it's pretty substantial. And then conversely, for the $5 per linear foot, those prices are substantially lower. Just want to point out that the subsidies below the negative subsidies correspond to cases that were already preferable, even without a subsidy, obviously. And so, just want to kind of highlight the fact that these subsidies really, in a lot of cases, are probably going to be necessary, and kind of the scenarios we presented here can be anywhere from up to $10 per linear foot, roughly, and that's the current cost at construction. And so we've been doing a lot of thinking, trying to decide how can we justify these costs, and who's going to pay for them, and that's I think maybe a question for more of the agency folks and people that are making more of the decision makers on some of these programs. And so what we did, the method we decided to take, which basically was a result of all the monitoring we've been doing, was basically trying to justify the subsidies based on nitrogen removal, the increased nitrogen removal that you see in a two-stage ditch. And so our approach was to, the first thing we needed to do was actually to convert the one-time subsidy necessary at construction to an annualized subsidy. And then you would estimate the increased annual nitrogen removal in a two-stage ditch over the conventional ditch. And then that will allow you to estimate the price per kilogram of nitrogen removed, and then you can compare that to other BMPs, which I know there's been some discussion about that already. So just a lot of our results were based on work by Sarah and Jennifer Tank at Notre Dame, and so their conclusions were that there was not really a noticeable change in in-stream nitrogen removal between conventional and two-stage, so we were able to neglect that in our analysis, and as Sarah discussed this in detail, but the end removal on the two-stage benches increased after construction, basically because of more surface area between water and the benches. And then they were discussing their analysis, how their nitrate removal estimates are related to the number of days of overbank flow every year. So that's the same approach we took. And so you actually use those. We used their denitrification rates and sort of some hypothetical ditch dimensions in conjunction with some, various numbers of days of overbank flow every year. And you just to summarize here, the nitrogen removal cost is that annualized break-even subsidy, and then divided by the annual N removed in the two-stage ditch. So, as you probably gathered by now, all this is getting a little bit complicated. So I just decided to present this as a table rather than a series of 100 graphs. So just to kind of, basically we just picked a number of different scenarios here, and just want to highlight a few of these. So the first column in bold, or the first row, in bold corresponds to a discount rate of 5% and a clean-out interval of 12 years. And you can see that you end up getting actually a nitrogen removal cost of, about 18 cents per kilogram. And I know some of you have probably figured out that these conditions in the first three columns are a situation that was just where the net present value of the two-stage ditch was just barely higher than the trapezoidal ditch. So the necessary subsidy was rather low, and so the removal cost was quite low as well. And you can see there are just a number of different scenarios here, and I mean it gets all the way to the bottom where this is a situation where there's not a lot of denitrification happening, just because there are only 10 days of overbank flow every year, and the construction costs for the two-stage ditch were rather high. And I mean, it could be completely sort of an unreasonable amount, if it's over $100. Obviously, if it's even over $10, it's probably out of the question. And also, I know this. I had to go through this a little bit quickly, and I'd be happy to share my communicate with people a little bit more to try to explain this. I know it's kind of a lot to digest, and certainly my thesis explains it pretty well, maybe a little bit too well. But just to summarize, there are certain situations, as I talked about, where two-stage ditches are economically preferable, just based on certain factors like clean-out frequency and interest rate and things like that. But I mean, the reality is that subsidies are probably going to be necessary, and there's going to need to be money coming from somewhere, whether it's the Nature Conservancy or it's Soil Water Conservation District or a watershed organization, things like that. And we think that the increased nitrogen removal is probably has the potential to be a very good way to justify those subsidies. But certainly more work is needed to justify the additional N removal. As Sarah mentioned, their estimates of nitrogen removal are probably fairly conservative, just because there hasn't been any work to quantify the benefit of floodplains during low flow when the water is not on the benches. So we've been doing a little bit of work here in Minnesota to try to get at that question, and kind of waiting on the results as of now. So thank you. Thanks for the time, and I'd be happy to answer any questions or take any comments. Please don't hesitate to contact me or Bruce Wilson or Joe Magner for any more information. Certainly be happy to provide more information. Thank you.
Thank you. Any questions for Jeffrey? Rebecca?
Yeah, Jeffrey, this is Rebecca Howard from the University of Wisconsin Extension, and you mentioned the benefits, potential benefits of nitrogen removal. I know you didn't monetize those benefits in this analysis, but did you talk about monetizing those benefits at all? I know that's a very complex issue, but something I continually see in these presentations is we look at we monetize the removal cost, but we don't talk about we don't monetize the benefits of removing the nitrogen and be able to do that kind of cost benefit analysis. What are we getting because we're removing the nitrogen? It seems like that's one additional piece of the equation. So I really like what you did, and I'm grateful that you're doing that work, and I'm just wondering whether you had any conversations about including monetization of the N removal benefits, like changes in property value, or what it actually takes to I'm thinking of phosphorus now, but the weed harvesting for phosphorus is a huge cost that would not be incurred if we were removing phosphorus. So those kinds of examples. The drinking water.
Yeah, the drinking water thing is really interesting. You make a very good point, and I haven't really done any work to address any of those specific sort of benefits that you mentioned. I think the idea was just kind of make a rough analysis that decision makers and policy groups and local government could use to say, hey, is this if we have to subsidize this ditch, is a $10,000 commitment or $20,000 commitment going to be worth it to our taxpayers, basically? And I think that's a discussion that definitely needs to happen. And I think the drinking water component is probably a really big issue. I know down in Des Moines, Iowa, they spend quite a bit of money trying to removing nitrates from their drinking water. So it's a very substantial piece of that, but we haven't done any work to kind of recognize what those benefits actually are.
I think there are a number of studies out, and Dan, you worked with, what was it, Joanna Mesa, correct? And looking at some of the benefits in terms of flood reduction, fiber fuel, anything that you might be able to take from a floodplain. And the actual benefits, if you take them to that next step, were pretty great, weren't they, in many cases?
Yeah, I think we made the services provided per square meter of bottom of benches, bottom of the channel, to be comparable to the wet. There has been a significant amount of work on trying to assess the wet to the tune of $1,300 acre per year, forever.
Yeah, that's really interesting. And that just shows there's so many other things other than what we chose to look at, which was nitrogen. The floodplain thing is a very good example. If you start adding on all these different services that you're getting from these BMPs, it starts to turn. It could kind of turn the tide pretty substantially in a hurry towards some of these practices.
Jane Frankenberger has a question.
Sure.
I think that's interesting. My first reaction is it completely a miracle that the Nature Conservancy has managed to get as many installed as they have. That's the overwhelming feeling I have, because now that we're starting to try and have
Yeah, I didn't have, there was kind of a limited amount of space to discuss all these different variables, and I definitely touch on that in my thesis. Be very happy to share that with you. But basically what we did for this analysis was just kind of, we modeled it on sort of some hypothetical dimensions which were kind of informed by our experience here in Minnesota with our ditch. And so I believe it was 10 or 12 feet wider on each side. So it ends up being something on the order of 2.5 acres per mile of ditch.
That sounds right.
Yeah.
There's no.
Is your thesis available yet if I email you, Jeff?
Yeah, it is, certainly. I've been waiting for, there's a university site where it'll eventually be published, and it hasn't been put on there yet, but I have it, certainly I can send it to you. So.
And Jeffrey, what about the spreadsheet so that we can use that here in Ohio, assuming a different number of years for the life expectancy,
Yep.
So we can put in our own cost amount, the curves, so we can make it more site specific. Is that spreadsheet available, and can you send that to us so we have it?
It isn't available now. I think I'm going to I'll have maybe have a discussion with Bruce and with Bill Lazarus about that, and it certainly isn't very user friendly right now.
Okay.
So I think that might be something we could look at doing. I mean, I'd certainly, my inclination would be that we want to share that with you, but I just need to talk to them a little bit.
Well, that would be great, because I think that's an important tool that our engineers in our counties are going to need to try and make a decision whether this is the best use of resources moving forward. So that would be great. If you need help getting that into a nicer format, perhaps we could help with that. But I think very important tool.
Yeah. Thank you.
Thank you. Thanks, Jeff.